determine the point or points that is or are closest to f of x is equal to the square root of x plus 1 from the point A, which is at 4, 0. Let's draw a little diagram of that. All right. So if you remember, a square root function, and this function is a square root that has been shifted to the left by 1. So at minus 1, I'm going to say this function probably looks something like that. It's a square root of x. So now we're going to put a point here at 4, 0. 4, 0 is maybe around here, right? 4 along the x, 0 along the y. So I just put it as 4. So the question we're asking is, what's the closest that you are to this? Now you might think, hey, just put a line straight up to the function. That might be the closest. But it could be maybe a line, instead of going straight up like that, maybe it's a point that's maybe somewhere here, right? It's not going to be all the way over here, but maybe there's another place somewhere along here where this point at 4, 0 is close. In fact, it isn't just putting a line straight up, just so you know. But there is a point, though, that we're going to try to find along this line, which is closest to 4, 0, right? 4, 0, of course, is like it's a point that's exactly on the x-axis. So we're going to try to see if we can figure out where that point is along this function. So let me turn this over to the class. What do you think we need to be trying to do here? What kind of equation do you think might help us to come up with a function that gives us that distance, and then we can try to minimize that distance? Because obviously, if we have the function, we can use the derivative of that to come up with the x value that gives us a minimum distance. How do you think I could come up with an equation for that? Over to you, folks. Let me get some ideas from you. Distance equation. Well done, Sarah. Well done. So let me remind you, I know you're in grade 12 now and you think, boy, that was like grade 10. Yeah, that was grade 10. Let me remind you what that distance formula looks like. All right, so this is the distance between 2 points. It's kind of like a Pythagorean equation. Distance between 2 points is the square root of, in fact, it is based on Pythagoras. It's based, and so it's the x1 minus the x2 squared plus the y1 minus the y2 squared. Okay, I'm hoping that looks familiar to you. Okay, and that's not the first time you're seeing that, because Sarah is right. It's the distance equation that we're looking for. You take the difference between your x's, square it. Difference between your y's, square it. Add them together, square root it. Okay, all right. So how does that relate to what we're doing here, right? What's my x1? What's my x2? What's my y1? What's my y2? Well, can anybody suggest what my x1 is? And can anybody suggest what my x2 is? Can anybody suggest find f of 4? Well, I guess we could find the f of 4. Square root of 4 plus, sorry, 4 plus 5. That's just going to tell us where the function is at 4, though, Adam. And not so sure that that's going to help us out, because, yeah, no, that's that. You know what? I prefer that you give me an idea than just sitting there blankly looking at the screen. So I'm thinking f of 4 is just going to tell me where the function is at 4. So maybe this point somewhere here, that's where it's going to be, at 4, right? So whatever that point is right there. And I'm saying that it may not be the point that's right above the 4. So I'm not so sure if that's going to do that. Wrong plan. That's all right. Can anybody suggest what I should be using for my x1, x2, y1, y2? That's what I'm trying to get. Adam has at least come up with an idea. I want to hear some more ideas, right? X1 could be 4. I agree. Good. So let's see now. -1 and 4 for x1 and x2. Why -1, though? Tell me why you're saying -1, Kushi. I'm just curious. By the way, I agree with Antaj. I agree with the x1 being 4. That I agree with. We could do, or x2, doesn't matter. We just have to be consistent. From the graph, Oh, you're thinking the point where I see what you're saying. So you're thinking, but then again, you're assuming that this point over here has something to do with where the the distance is that we're going to. But remember, we have to measure to this distance right here. And by the way, let me give you a little idea here. We know the coordinates of this point as being 4,0. Right? That's what it says right there. 4,0 is the coordinate of the point. Right? So let's consider, so yes, we do have a potential x and we do have a potential y. We have those two things, right? The x could be 4. Let's say the x1 could be 4, and then the y1 could be 0. So can we agree on that first of all? That we do have a potential x and we do have a potential y. It's the x2, good, thank you, Sarah. It's the x2 and the y2 that we're going to have some trouble with, right? And so does anybody have an idea what we could use for that? Now remember, this is the equation right here, right? I'm going to give you a little clue then. How about we do this? We say that, instead of saying f of x, I'm going to say that y is equal to x plus 1. Does that kind of point you in the direction? All right. What are we going to use as our x? Think back. Okay, let's do this. Think back to when you're doing first principles, right? And one of the first principles, let me show you one of the first principles approaches that we took. We said that we could use the f of x minus the f of a over x, the x that you have minus the a. Remember that? Look familiar? See if maybe that might be a clue. And by the way, if the f of x just refers to the function itself, whatever the function is, we're going to use that. The x is just x. We're just going to use x for x. Okay? So maybe, just maybe, the f of a and the a could be that 4. Sorry, 4 is the a and the 0 is the y right here. So we know that that's on point. So this is if you're trying to do if we're trying to do a limit, or sorry, a derivative. Let's erase that for now. Erase, come on, erase. Let's try that again. Erase. Okay. So equals square root of. What can I use for x1? What can I use for x2? What can I use for y1? What can I use for... Let's go with the y1, y2 first. How about if I said for y1 that I was going to use the... Remember, look at what y is. Here's what it says y is right here. What am I pointing to? Y is the square root of x plus 1. That's what y is right there. Square root of x plus 1. Right? We can call that. So let's say we're using that as our y1. What are we going to subtract from that for our y2? Isn't that the function? Of course it is, Taj. But we said that y is the square root of x plus 1. When we were doing the thing I just had on the board a while ago, the f of x and the x in the function, we just use the actual function itself. Do you remember that from when we're doing the limit stuff? Right? Okay, so why don't we use that as our y value and then subtract from that, the function, the y value that we are measuring to, which is what? What are we measuring it to? What's the other y value? We talked about the other y value already. What's the other y value that we're... 0, thank you very much. Squared. Plus, what do you think I'm going to use now for my other x? All right, remember, I have to have something which is related to this square root of x plus 1. Whatever is first here has to be first here as well. What am I going to use here in the first position? Anybody? What do you think I'm going to put there? And then we're going to minus from that, obviously, the other x value that we have, which is the 4, right? Well, what are we going to put there? 0? No, because that's not, remember, 0 is a y value, right? Just remember that. So we already have that 0. Well, maybe I had that from before. That was a couple of times before. But what are we going to put here? Right, so we've done, so what we've put in is the y1 minus y2. That's what we've put in so far. Let's get the x1 minus x2 now. What are we going to put for the x1, which is related to this square root of x plus 1? All right, let me back up the truck a little bit here, right? Because I want to make sure. What if I said to you, would you isolate x from the square root of x plus 1? It's not just isolating, it is x. Okay, let me take you back a bit, right? Let's say I asked you to find the slope on the square root of x plus 1 at when x is equal to 8, right? But let's just use that as an example. I want to sort of see if you can capture this and figure this out for yourself. Well, first of all, when x is equal to 8, we have a point 8, 3. Can we agree on that? If I put 8 into that, 8 plus 1, which is 9, square root of 9 is 3. Okay. Would you isolate x from this? Okay. So would you first of all agree that we can now use the f of x minus the f of a over x minus a? Then, of course, we're going to find the limit as x approaches a. All right, that part is the second part. But what are we going to put for f of x? Let me just make sure that we follow this. What are we going to put for f of x in this case? Think back to first principles for a bit. What did we put for the f of x? In this case, what are we going to put for the f of x? The root of x plus 1. Thank you very much. So the root of x plus 1 minus the f of a, the a being in this case, the 8 is what we're putting in, but the f of it is actually 3, right? That's the y value, okay? Divided by, what did we put at the bottom? Does anybody remember? For the x minus a, what did we put? Nobody remembers what we put for the bottom? We put x and minus from that the 8, right? I guess somebody remembers that. Just put a generic x minus 8. Thank you, Sarah. Okay, so based on what we just did, I'm going to erase all of this stuff now. So we put the function itself, right, minus the value of the function at 8, so that's 3, over just x, generic x, which is the x value, minus the x value that gave us that 3. So where's the 8 from? Tomaleo is asking. I made up 8. I just said what if back in the days when back when we're, and I use 8 because 8 is a convenient number to use because the square root of 9 is 3. That's why I chose 8. But back when we were doing first principles, right? And we had this f of x minus f of a over x minus a. We said f of x would just be the function itself. So the x plus 1, the square root of x plus 1, minus what is the value of the function at the point that we're trying to measure this at? Turned out to be 3. That's that's when you put the 8 into that, you get 3. So I put the 3 there, over x, generic x. So this is generic function. F of x is the generic function over generic x minus the value of the function, sorry, the x value of the function that we're trying to measure. So we put 8. All right, so that's where the 8 came from. Okay, Tamala, do you see where I'm getting that from now? Is that good? You said okay, so I guess you're okay. Okay, fine. So let me erase this and come back to what we're doing over here. Give me a second to erase this. I'm going to erase all of this here, actually, because I want us to use the same logic for this. All right. So now I gave you the first part of this, which was the square root of x minus 0. So that's like saying generic generic y, which is f of x, square root of x plus 1, minus the particular value of y that we're talking about, which is the 0. What do I put for this over here now? Right? What do you say, folks? On the other, what do we put on the other side? I'm asking you for your help now. Anybody? Okay, let's see. X minus 4. Thank you very much. That's exactly right, Ashland. Right? So generic y value is let me circle it. Generic y value is this guy right here. minus the specific y value that we're talking about, which in this case is 0, because we're measuring it to 4, 0, plus generic x value, which is just simply x, minus the specific x value that we're talking about here. This will give us the distance to any point on this function. Right now, we want to know the distance from the function to 4, 0. We just put the different values of x into this. Where when x is 5, when x is 10, when x is 52, when x is whatever value of x you want to put in. If I want to know what the distance is to 4, 0, I just use this. Right? This is going to give us the distance to any point along the function. So if I put in x as being, I'll just make up a number right now. If I said x was 1, right? Let's say I want to know how far it is to get to 1. So I'm going to mark off 1 right here. When x is 1, all right, so let's say I want to go from when x is 1 right here. I want to go from that point to my 4, 0. Then I just put 1 into this function. This function is the distance to 4, 0 from any point along this curve. If I wanted to know when x was let's make up a number, when x was 7 or 10 or 52 or whatever, right? Any point I want to measure to the 4, 0, I would use this exact formula right here. I just keep changing the value of x. But in generic terms, this is what it is, right? This is the general formula for the distance to 4, 0 from the function square root of x plus 1. Okay, does that clear it up for everybody? Hopefully it does. All right. Now, so here's what I'm going to do now. I'm going to square this plus the square of that. I'm going to take the square root of that, and then I'm going to take the derivative of that and see if I can figure out what's going on here. Okay, Adam and Sarah and Tomalea, thank you very much for responding. Okay, so what happens when I square the first bracket? The square of, now remember, if I'm minusing 0, all I have really there, why the derivative? Okay, we're going to get the derivative. Thanks, Adam. Thank you very much for asking that very pertinent question, very relevant question. Because after we simplify this function, the question is, what value of x gives us the smallest distance? And let me go back to the question to show you that. Determine the point or points that is closest to this, to the 4, 0. So because we're trying to find a minimum value on this function that gives me the distance between 4, 0 and some point on the graph, that's why we need the derivative. Does that make sense, Adam? We need the derivative to minimize the distance between that point and, okay, good. Thank you. Okay, let's keep going. So the square root of, help me out, folks. What happens when I square that first bracket? What am I going to get by squaring that? You're welcome. What do I get when I square that first bracket? So it's the square root of x plus 1 minus 0. The x plus 1, correct, because this is minusing 0 doesn't do anything. You're squaring a square root. You're going to get just simply x plus 1. Now, the second one is a little bit more work. What about x minus 4 squared? What is that? Thank you, Fernando, and thank you, Adam, by the way. When I square x minus 4, give me the correct, because I know sometimes students mess this up. I don't expect you to, but I know sometimes students mess this up. So x squared, good. Okay, Ashwin, thank you, Fernando, and thank you, Stephen, and thank you, Richard. So it's plus x squared minus 8x plus 16. Okay, all right, hopefully everybody follows that. Well, let's simplify this, all right? So I'm thinking x squared, excuse me, minus 7x plus 17. I think I did that right. X squared minus 7x plus 17. Yeah, that seems okay. And this is my distance formula based on the value of x. Again, I could figure out the distance to any point on this curve from 4, 0 by putting the x value into this, right? Any point at all. But really, and as Adam was asking, I need to find a derivative to know what is going to be the distance which is the shortest distance. That's my goal now. So I'm going to find my d prime of x. All right. And of course, well, before I do that, let me set this, let me make this, oh, hold on. Let me make this equal to something to the power of a half. So d of x is equal to x squared minus 7x plus 17 to the power of a half. Not minus a half, but a half. Not sure why I said minus. Let's see if I can. All right. To the power of a half. Okay. So we're now going to find the derivative, which of course is a half. Actually, after a while, I think everybody knows this now. It's going to be 1 over 2 times the square root of the x squared minus 7x plus 17, because you're going to have this thing being raised, you're going to have half times this to the minus a half, so this becomes a denominator, and then you're going to have 1 over 2 times this thing, and then on top you're going to have the derivative, which is 2x minus 7. Okay? I hope everybody's okay with that. The top is going to be 1 times the 2x minus 7, but it's just simply going to be 2x minus 7. So what that means is that we now have to set this thing equal to 0. And again, it doesn't matter what the numerator is. Sorry, that's rubbish. It doesn't matter what the denominator is. It matters what the numerator is. So really all I'm going to focus on is the 2x minus 7 equals 0. And therefore 2x is equal to 7 and x is equal to 7 over 2. Okay, let me take you back now. Determine the point that is closest to this. So what does this x value tell us, right? What is this 7 over 2? Is that a distance, or what does this represent? Give me in plain language what that 7 over 2 really means to us, right? What does that mean? The 7 over 2 means what? Come on, folks, help me out. What does 7 over 2 mean? I need to get some reaction from the room here. All right. X at 7 over 2 is the closest. Correct. Now, the question didn't ask us, let me see what the question asked us, because I want to make sure we're answering the question. Determine the point that is closest to f of x equals that from it. Okay, so we have the x value of when it is closest. So we need to give this, so do we need to find, of course you do. Of course you do, Sarah, yes. And that would be an actual coordinate now, because that's what it says. Find the point or points, right? Turns out there's only one, by the way. That's closest to it. So we have the x value where it's closest. So we need the y value. So how am I going to get the y value? Not just Sarah, but how do I get the y value? How do I get that? Because that's part of the question. We haven't found the y value yet, right? We have the x value of being 7 over 2. Use the x value and do what with the x value? Substitute it. Okay, substitute it where? Into what? Into the derivative or what? Into the original. Thank you very much. It's the f of 7 over 2, the original function, not the derivative, but the original function. So we're going to be talking about the square root of 7 over 2. Is it plus 1, minus 1? Plus 1. Hold on, did I write something wrong here? X squared minus 7. Oh, yeah, no, I didn't. Yeah, okay. So 7 over 2 plus 1, square root of this. Okay. And of course, you can just find a common denominator from that. Square root of 7 plus 2, 9 over 2. Right? And another way of writing that is to write 3 over root 2. So here's my coordinate. My coordinate is 7 over 2, 3 over root 2. I found the square root of 9 over 2, and that works out to be 3 over root 2. Okay, there's your answer. There's your x, there's your y. That's a point that's on this graph. Turns out it's not a point that's straight up. I know some people think it just got the straightest, the straight line should be the closest. It's another point. It's somewhere close to, but not quite straight up. So 3.5, somewhere around there, would actually be a closer point on the graph. Okay. Moving right along, moving right along. So now, hope everybody is. Can I go back down? I sure can. I will. I am recording this, Ariana, so you should have the video for later on. But I don't mind going down at all. Okay. Let me know when that's enough for you. Are you good? You're good. Okay. Let's move on. This question: the perimeter of the cross section of a package, and this, not that the figures are necessarily the same figures that Canada Post uses, but they do talk about girth when they are determining whether a package can be shipped with them, right? And here's how this works. So the perimeter of a cross section of a package that is a rectangular prism is called the girth. For courier, we'll only accept a package if the sum of the length and its girth is no more than 300 centimeters. What is the volume of the largest acceptable package volume of the largest acceptable package with a square cross section? I am not going to try to draw this at all. Maybe I can find something in here which is three-dimensional, but I would not attempt to. Maybe I can find something, but I'm not going to, because you're just gonna start laughing at my diagram. So you're gonna have to try to picture this yourself, right? It's a rectangular prism. What I will do is try to show you what the girth is. You know what? I'm going to try my best, folks. Hold your laughter for me, please. So it is going to be something looking like this. Well, I don't know. Something looking like this. Right? Yeah, I see. Yes. Thanks a lot, Ashra. Thank you. I appreciate that. Anyway, um, the girth would be the distance around the sides like this. Right? That's the girth. And then they're going to take that perimeter around this cross section and add it to this line, the length. They're putting those two. Okay, Sarah. They're putting those two together. So these are two distances. A perimeter around this edge here and adding that to the length. So let me go back and show you where it says that in the question. The sum of the length is what I'm tracing out here, and the girth, which is what I'm tracing out here, the perimeter of one edge of this package. And they're saying that when you add those two together, it cannot be more than 300 centimeters. Now, I can't remember exactly what Canada Post used as a limitation, but that's how they come up with the, the limit, right? Can't be more than 300. So, what's the volume of the largest acceptable package if this thing has a square cross section? So it means that this thing that I'm pointing to now, this thing that I'm putting a circle on, is actually a square. So let me sort of give you a start here. I'm saying that if we call this x here, this is also going to be x. And let's call this distance here or y. Right? Let's call that distance or y. So when you sum all of these distances around this square on the end, and you add that to this distance, the length of the package, 300 is the max, right? So let me put this down and say that let L equal the length. Let's do a let statement. And let X be the, oh, no, not L, sorry, Y, sorry. Let Y equal the length. Let X equal the width. And that's the width of one end. And it's a square, so it's going to be the width and length of one end of the thing. All right. So far, so good in spite of my very crappy diagram. Okay, so far, so good. Okay, everybody on the same page with me here. All right, let me check in. You know, I like to check in from time to time. Okay, Sarah, Lisa's checked in. But how about Alicia? And how about Christopher? And how about Ella? How about those people? Christopher, okay. How about Ella? Where's Ella at? Is Ella there? Good. Okay. All right. Good. Probably he says. Okay. Please don't blame it on my diagram. All right, please don't do that. I'd be hurt. Anyway, so think about a rectangular prism. Think about a box that has a square base. Think about it that way, right? I've tried to put that onto the diagram. So I took this box and stood it up on the table that it's sitting on. Then the part that's sitting on the table is a square, then it has a height. Let's put it that way. Think of it in those terms. I wish I had a diagram that I could show you a little bit more, but I don't have any 3D, or maybe I do. Let's have a quick look here. Let's see if I can find a rectangular prism. Okay, okay, Sarah, thanks. Folks, let's just work with me here. Let's just try to picture this in our mind. All right. So what are we saying is no more than 300, right? What exactly are we saying? Can we put that in mathematical terms now? What is it that's no more than 300? Can we put that in some sort of a mathematical equation? So y plus x squared is what Adam is saying. And 4x plus y is less than 300, as what Stephen is saying. Now, which is right? Are they both? Well, they can't both right because they're saying something different. So who is right then? Or is either one of them right? That's the question. I think Stephen is right. Adam said, oh, you're changing your mind then, Adam. Honestly, okay. All right. Yeah, Stephen is right. Stephen is right. Because what we're doing is we're saying that the girth is when you take all of these x's and add them together, and there are four of them, right? It's a square, so you know that the perimeter of a square is 4 times whatever one side of the square is. So that 4x plus the w, sorry, plus, I keep saying w, plus the y, it says must be less than or equal to 300. Okay, that is what we're saying, right? Now, it does mean that also x and y have to be positive, so we can also put some limitations on that, right? And we should also note, let me write that down. X has to be greater than 0, and y has to be greater than 0. Greater than or, well, not greater than or equal to, but greater than 0. We know that. But we also know that we can rearrange this thing here. Let's write that down. That y must be less than or equal to 300 minus 4x, right? That's also true. And that this thing, 300 minus 4x, must be also greater than 0, right? This value of y must be greater than 0. Okay, let me erase this part right here. So where else do we go, folks? It's 2:21. We have about 19 minutes left in the class. We need to finish this question. All right, where else do we go with this? So we know that we have an equation that links together the x and the y. It must be less than 300. We can just set it equal to 300 for now. But what else do we do with that? Right? What else do we do with that? All right, is there something? Remember, what we're trying to maximize, this is a maximization problem for this optimization here. What we're trying to maximize is volume. That's what we're trying to maximize. All right? So do we have an equation for the volume? Is the question I guess I'm asking. Can anybody suggest a volume equation? All right, I'm looking for I'm not going to write it down until I hear it from somebody. Folks, come on. I think you can come up with a volume equation here. So Taj is saying x times y. Javier is saying 2 times x times y. Ashran seems to be on the same page with Taj, but Javier is not. Javier has a different point of view. And Kushi, oh, a lot of people are on the X times and Adam. Oh, okay. So I'm gonna have to say, Javier, that I think they're outnumbering you. And it's not that it's always democracy when it comes to math. I mean, sometimes some things are just right, and whether you're in the minority or not, that's not the issue. But I'm gonna have to agree with what people are saying. It is x squared times y. So let's write our volume equation down. All right. Our volume is x squared y. Okay. But we know we can't do a derivative with two different variables. So what do you think we need to do to slim this equation down to one variable? Any ideas on that? Sub in the y. Okay, good. And we have a y as being equal to 300 minus x. Let's put that in then. So v is equal to x squared 300 minus 4x. That sounds like what Sarah is saying to me. I don't know how it sounds to you. That's what it sounds like to me, right? The 300 minus 4x represents one way of writing the y down. And we're putting that in as our y. Okay, so we're looking at a cubic function here, apparently. Okay, how do you recommend that we... So now we have a function that will tell you what the volume is at any point in time, right? Just put in the value of x. It tells you what the volume is at that point in time. What do you recommend we do with that volume equation? So it's a v of x function. Volume based on the distance across the side there, x squared 300 minus 4x. What do we do? Now, file it out and then take the derivative. I like that, Taj. I mean, you could use the product law, but who wants to use the product law when they don't have to, quite frankly? So I would say I like what Adam is saying. So I'm going to file it out as he says. So 300 x squared minus 4x cubed. And he further said that we now have to take the derivative. He has a question sign on there. That's what I did, but Taj said it. Okay. All right. Okay, so you beat Taj to the punch on that one. All right, so let's find the v prime of x. That should be pretty easy because it's a polynomial. So that would be 600x minus 12x squared. 600x minus 12x squared. Yeah, okay. And what do we do after that? There's our derivative. Set it equal to 0. Okay, so I did. I set it equal to 0. Okay, but it's a quadratic, so how do we solve a quadratic again? Walk me through that whole process. How do we solve a quadratic again? Help me out. Common factor, good. And I'd say the common factor here looks like it's 12x to me. Okay, and to me, that looks like it would probably be 50 minus x. I could be wrong, but you will tell me. Am I right? 50 minus x? Is that good? Thank you, Alexander. Okay, equals 0. So it looks like I have two solutions, right? X is equal to 0 and x is equal to 50. So should I take both of these solutions that we got? Are they both good or is only one good? And what do we do here, folks? Right? Why don't we use the 0? What's wrong with the 0? Restriction, absolutely. We said x has to be greater than 0, which with 0 is not. So 50 makes more sense. So let's go back and look at the question again to make sure that we're going to... It always, when you have these questions to do, you always go back and say, did I answer the question? Right? Is the 50 the answer? Well, let's find out. Here's the question. What is the volume of the largest acceptable package with a square cross section? So x equals 50 means what? What do we do with that? Right? Have we answered the question yet? I'm going to say no. We need to find a v of 50. Good. We absolutely need to find a v of 50. So that's pretty simple. We just simply put that into the function. And the function originally was 350 squared minus 4 times 50 cubed. And I'm going to leave that with you, right? Because I'm sure that you can do that. We have about 12 minutes left. I am actually going to tackle, unless anybody has any questions, I mean, you can do that on your own. You don't need me to do that with you. And that would be the answer, by the way, the largest possible volume that you could have. And it would be in whatever units would make sense for this, which would be centimeters. All right, so that would be in centimeters. Okay, but what I wanted to do in the last couple of minutes of the class, and again, tomorrow, please come with, thank you, Ariana. Please come with your questions that you have about the problem set. It's on the Unit 3 assignment. So go to the MVL, the Math Video Library, look through those questions as somebody else was doing yesterday, who said, can I get a little help with this thing here? And I'm quite happy to answer those emails if people are emailing me about things like that. So thank you, by the way, Ariana, for the answer. So let's get to this question now. This was a question which was on a homework, and I did mark the homework, and a lot of people got it. So if you did, sorry, where's the problem set again? Okay, let me tell you what, let me finish the question. Okay, let me put a link in the chat to the Math Video Library. Go to the Math Video Library and look for grade 12. Actually, I'm going to give you the link that takes you right to that page. Just give me 1 second here. Calculus and vectors. Okay, so I'm going to put this in the chat right now. There's the link to the Math Video Library is on the D2L. All right, if you go there, Adam, and you go down to Unit 3, which is the one we're on now, and look for the assignment, the unit assignment, I think it's called. Right, so just go down to Unit 3. Okay, there you go. All right. And the answers are there as well. So you can try it out on your own first. And if you are stuck, then tomorrow you come. Now, tomorrow we could start Unit 4. If everybody is comfortable with all the questions on there, then we just go to Unit 4, right? Because, we have a limited amount of time here to get through a lot of content. We haven't even touched on vectors yet. So we're just going to go to Unit 4 if we don't have any questions. All right, let's get back to work. Let's get back to work in the time that we have left. All right. So here's one of the questions that was on a homework, and a lot of people got it right, but some people struggled a little bit with it. And I thought, why not just spend a few minutes on it? They give you an equation for height. All right, so that's a position. It's a position function. And they tell you that height is given by this function based on the time. Find a formula for the vertical acceleration of the softball at time t. Well, as you already know, acceleration is a second derivative of the position function. So that part wasn't that hard, and I'll just do that very quickly here. So the h prime of t is going to be equal to 15 minus 10t, right? And the h double prime of t is going to be equal to minus 10. So all that means is that this, softball is accelerating at a constant amount of minus 10 meters per second. That's all that means. Okay, so that part is that's done. What's the initial velocity of the softball? Again, I don't think many people, the third part of this is where some people had some trouble. So I'm going to get to that in a minute. Initial velocity of the thing. Now, here's my velocity function. So initial just means what happens when t is equal to 0, right? So put 0 into that, you're just going to get 15. Okay, now let's get to the third part. You're welcome, by the way, Adam. Let's get to the third part. What's the vertical velocity of the softball at the time that it hits the ground? So what you need to be thinking of is, when does the ball hit the ground? Because if I know what that time is, then I can come back and put that into the velocity function. Okay. The original function was a position function. So if I want to know when it hits the ground, what I'm really asking is, when is the height above the ground equal to 0? So I should have taken this 15 minus 15t minus 5t squared and set that equal to 0. Okay? Because at that time, the height above the ground is 0. Just solve for t. So I'm going to factor out the 5t. That leaves me with 3 minus t here equals 0. And therefore, there are two times when the height is 0, 0, and 3. Well, one of them is where at the start, right? Right at the very start, I obviously was on the ground. And then 3 seconds later, I'm back on the ground. So think of that ball being shot up, or softball, whatever it is, being shot up in the air, coming back down, and 3 seconds later, it's on the ground. But the question is not when does it hit the ground? The question is what's the velocity when it hits the ground? So I'm going to go to my velocity function, which is my h prime of t, and put 3 into that. So 15 minus 10 times 3. And you work that out and get that answer. Okay? The other one that some people struggled with, and I'll just end the class on that one, is this one here. All right, this was number 3. A car is 80t plus 1 over t squared. So it's a position function. It tells you exactly where the car is after time t hours. Where's the car and how fast is it traveling when the acceleration is 16 kilometers per hour squared? So I have a position function. I need an acceleration function. So I just simply need to turn my position function into an acceleration function so I can find out when that is equal to 16. So I'm going to call this my, let's see, no, not h. Let's just say f of t. F of t is equal to 80t plus 1 over 10 t to the power of 5. Here's my velocity function, which would be 80. 5 times that, that's going to give me, what is that? A half t to the power of 4, right? And then my acceleration function now, double prime of t, is going to be equal to 2t cubed, right? I'm going fairly quickly because we're running out of time. So just make sure you can get those derivatives on your own. That's my acceleration function. And it does say when acceleration is 16. So don't put 16 in for t. Set the function equal to the 16 and solve for t. Okay, so let's divide through by 2, which is 8. And let's find the cube root of 8, which of course is 2. So it means that at 2 seconds, my acceleration was 16 kilometers per hour squared. But that's not the question. The question is, where am I? And how fast am I traveling? So I now need to take this answer of 2 and find, first of all, the f of 2. And I also need to find the f prime of 2. Why the f of 2? Because the question wants to know where am I? Where is the car? And that's a position question. So sometimes the questions are getting you to get an answer in one derivative and take that answer and put it into another derivative or in the original function. So that's exactly why I'm doing this question with you, because this could be the kind of question that I put on an assignment, along with the other stuff that you have there already. So the f of 2, of course, is just simply putting 2 into the function, which is what else? 80t plus 2 to the power of 5. That's just work that out and finish that up. With 10 to the power of 5, right? And this answer answers the question of where. That's what this is going to answer. Where am I? How far am I past the gas station? The second one, you're going to do that, which is the 80 plus a half of 2 to the power of 4. When you get that answer, this answer is a question of velocity. How fast am I going at that point? So when my acceleration is 16 kilometers per hour, I am this distance away, once you come calculate this, from the gas station, and I am traveling at this velocity, whatever this works out to be. Okay? Instead of 1/2. Is it really? Well, the first derivative was 1 over 10. The original function was 1 over 10 times 5, so that would be 5 over 10, which is a half, t to the power of 4. And then, okay, go down. A half Oh, right. Yes, yes. Thank you. Thank you very much. You are absolutely correct. So it's 1 over 10 and then 2 to the power of 5. Yeah, you're right. Um, but I have 1 over 10 though. 2 to the power of 5. Go down some more. Something else is wrong. Instead of a half t to the power of 4. Did I do something else wrong? I mean, if I did that, you help me out here, folks. Are we good? Is that not right now? Did I correct my error? I think it's fine. Okay, thanks, Fernando.